Good evening, good evening, good evening, my dear NEET warriors. This is your Capto, your Captain Shreyas, and I'm going live on the Vedantu NEET English channel. And you are on station 0 of the NEET Express. Yes, the journey begins for NEET 2025, the final journey. And this is the last train which is leaving station 0, station 1 on our platform. And we will be having some amazing thing coming up next week in terms of your PYQs and problems. So stay tuned on the Vedantu NEET English channel, which is the #1 English channel in the country. In this particular lecture of Station 0, after having an amazing blast for basic maths, we are going to do photons, wave particle duality, and photoelectric effect. One of the most important topics from your NEET perspective. Also, very high frequency questions come from these particular topics. So let's begin. This is your Captain Shreyas. Hi Sneha. Hi Susmita Disha. Let's play. Welcome Pratibha. Susmita Emperor Rohit. Good evening, Evening Star. Hello, all the warrior Pandus. WP. All the warrior Pandus. Whistle Podu. Yep. Hi Maya. Hi Krishna. Hi Jasmine. Hi Latha. Nice to see all of you. Lot of new students as well, and maybe you are watching recorded and now decided to watch live. No issues. So let's begin. In today's lecture, we are going to study something called as a dual personality disorder of light, and then we will see how that led to finally the discovery of photoelectric effect by Einstein, and how he won Nobel Prize for it and not for a theory of relativity. So you might have seen that some people have dual faces. In the house, they are very quiet, silent. Mom is there, dad is there, nothing they are saying. Like this, head down, they are walking. Meet them in the school, full heaven only. Like one shaitan, like one rakshasa. Okay, they will be jumping on somebody's head and pulling that hair out. They will be, screaming, they will be doing some nonsense. So, that is the dual personality. Now even light has that dual personality. So let's talk about that first, and then let's slowly move ahead. See, my dear warriors, when you talk about light, it has something called as dual behavior. The dual behavior, and one is basically the particle behavior. Sometimes it behaves like a particle, and you will see sometimes it does behave like a wave. Sometimes it behaves like a wave. Okay, now what do I mean by that? See, there are some characteristics of a wave. What do you mean by, okay, this is a wave, okay, this is a particle? There are some peculiar characteristics, like how you know, oh, this is a donkey, okay, this is a zebra, oh, that's a kangaroo, okay, this is an elephant. There are some characteristics. If it has a trunk, it's grey in color, it's huge, it has 4 legs, a teeny mini tail, and walks slowly. So yeah, that's an elephant. Zebra, oh, it has stripes, okay, it looks like a horse and it can run very fast. So some characteristics are there. So for a wave, the characteristics are like reflection of light. Then you also have refraction of light. Then it can also interfere with each other. So interference is a peculiar characteristic of light, or even bending of light around corners or holes. So you have diffraction. All these peculiar characteristics are shown by light sometimes, but also sometimes light can impart a force. It can impart a force, just like when a cricket ball strikes the bat, it imparts a force. It also possesses momentum. And these are peculiar characteristics of a particle. Now this particle of light is basically called as the photon. Particle of light is basically called as the photon, and the wave of light is nothing but electromagnetic in nature. It's a electromagnetic wave for which there is a separate dedicated chapter in your NCERT and NEET. Electromagnetic waves, electric fields and magnetic fields go perpendicular to each other at the speed of light. So the particle nature of light is basically called photon. A lot of people think photon is one dot or one circle or a sphere. No, nothing like that. Nobody knows how a photon exactly looks like. Is this clear, my dear warriors? Yeah, awesome. Crash for DNA, I'm not really sure, Ashwin. I'll let you know. Hi, Kumkum. Welcome, Charanya. Yes. Hello, Vandana. Nice to see all of you back. Now we are not going to focus on this because this dedicated chapter is there, wave optics is there, all these dedicated chapters are already there for light. We are not going to focus over there. We are going to focus on this particular part, which is the photon part. So let's discuss the photon aspect of it. So the photon, which is the particle of light, this particular particle of light, number one, first important thing about it, it travels at the speed of light, which is roughly 3 into 10 to the power 8 meters per second. 3 into 10 to the power 8 meters of second. Number two, a photon is a packet of energy, often in physics word you call it as a quanta. It's a packet, like you buy a biscuit packet or a packet of some powder or a packet of some juice or a packet of some, I don't know, any chips. So this energy of light is sealed in packets, like how chips or biscuits are put in packets. The energy of light is sealed in packets. Each packet is basically a photon. It's a quanta, it's a packet or a quanta of energy. And energy of light does not go continuously, rather it goes in packets. Imagine these two scenarios. You have a pipe of water and you have connected it to a tap, let's say. You have connected it to a tap and water is coming out of it continuously. One scenario. Second scenario, you again have a tap of water, but what you do is you fill water balloons, and these water balloons you throw it on somebody versus you spray that water on somebody. This is continuous flow, whereas here also same energy is there, but you are collecting it, putting it in a balloon, packet, quanta, and throwing it. Collecting the water, sealing it, throwing it, collecting it, throwing it, okay, after sealing. So this is how exactly light travels in particle nature. It is not a continuous flow of energy. Is this absolutely clear? Vandana, question practice series starting next week. All the details by the weekend. Okay, by the weekend I will explain. I will let you know all the details. Okay. This much is clear. So it is in the form of packet of energy. Now, how much is that packet of energy? That packet of energy, the energy of a photon, is given by a constant h into f, where f is the frequency of the light. F is the frequency of the light, and this h is basically called as the Planck's constant. Planck's constant, who has a value of 6.6 roughly into 10 to the power -34 joule second in SI units. Because we know that the speed of light also happens to be frequency times the wavelength, you can also rewrite this as hc divided by lambda, because f is c by lambda. F is the c, lambda taken downstairs. So this will also do, or that will also do. That's perfectly okay. So this is something which we need to block. Okay, energy of a photon is a hf or hc by lambda. Any one of them will do. Now, often what happens is you are given wavelength in Armstrongs or you are given wavelength in nanometers, and usually this quanta of energy is not very big, it is very, very small. So joules is not the right unit for it. Like if I have to measure the wealth of Ambani, I will not write it in terms of how many 100 rupees does he have? No. How many 1,000 rupees does it have? No. How many lakh rupees? No. I will talk in terms of billions, millions, like that, right? So we need a bigger unit. Similarly, if you want to measure how small is this microorganism, I can't say how many kilometers is this virus. It will be like 10 to the power minus 7 kilometers. Be like, oh, you will not get a feel. 10 to the minus 7 kilometers. Why will you measure kilometers for a microorganism? No. So same way, this energy is very small. So usually what you do is, to measure this, you write this particular number, which is 1280, okay, and you divide it by lambda, but this lambda has to be in nanometers, and the final answer of the energy that you get is in electron volt. This is something which is very important. You can also write it as 12800, whole thing divided by lambda, but then this should be in Armstrong. Armstrong is 10 to the power minus 10 meters. The answer is again in electron volt. So very useful formula for practical calculations. This will save you a lot of, sorry, I think I wrote 1280, it is 1240, my bad, not 1280. So sorry guys, my bad. This is 1240, this is 12400. All right, is that right? All right, everyone? Yeah. Yes. 1240 happens sometimes. Okay, so this is useful for calculation purposes. Now, this is not all. There are more properties of a photon. When we measure the intensity of the beam of light, intensity of a beam of light, that is basically how much energy is there per unit time, per unit area. So strictly speaking, the energy of that particular beam of light will be number of photons multiplied by energy of basically each photon, the whole thing divided by the time which you are considering and also the area. So this will just become N hf, energy of a photon is hf, divided by T and then divided by area. So this is another way of writing the intensity. Remember, the units of intensity will be watts per meter square. Makes sense. Energy per unit time is watts, area is per meter square. So when you have light which is coming and you are considering an area of cross section A, so how much energy of light is coming per unit time, per unit area, that is the intensity of the light. So this is how it is calculated. This is the formula for it. I just block that off also. What is this peculiar term which you are seeing over here? This term which you see, N by T, is the number of photons per unit of time. This is the number of photons which are coming through per unit of time. This is also either given to you or you will be asked to find that out. Okay, one of them. Either it is given to you or you will be asked to find that particular thing out. Yes, this is next important thing which you should be aware of. Next, the momentum, remember, particle of light is photon. Photon will have some force, it will apply some force, it will have some momentum. Yes, momentum of a photon, lot of people will say, sir, simple formula sir, for momentum of photon, P is equal to m into v, where this velocity is the speed of light 3 into 10 to the power 8 meters per second. How many of you thought this? If you thought like that, wrong. You cannot use this formula of m into v. It is not applicable anymore for this. Reason being, the mass of a photon is basically zero. It is a massless particle. The rest mass, don't have to worry about what is the hell is rest mass. It is in terms of relativity and all of that, where in relativity it says that if mass begins to move, the mass changes. So let's not get there. Just remember, in general, if you see a photon at rest, the mass of the photon will be not tending to zero, it will be equal to zero. Okay, it will be equal to zero. So 0 multiplied by any number will be 0. So momentum will not be there. But then it contradicts the whole purpose of defining the photon as a particle, because a particle was supposed to have a momentum. And you are saying because mass is 0, momentum is 0. So then how the hell is it a particle? So you cannot use this formula. So it was finally found out the actual formula that you can use for the momentum is the Planck's constant divided by the wavelength. Planck's constant divided by the wavelength. You can also repurpose this formula like this, h by lambda. You put c on the top, c below, no change at all, and multiplying, dividing by c. And you can put hc by lambda, and this is 1 by c. What is hc by lambda? I think we just got it over here. Hc by lambda is the energy of the photon. So therefore, the momentum alternatively can be written down as the energy of a photon, the whole thing divided by c. This also is the correct formula. Either you use this or you use this, both will work. H by lambda, or energy of the photon divided by c. Is this clear? Yep, very good. This is very, very important, my dear warriors. Awesome. Now that we have seen all these properties and how the mass of a photon is 0, but it has momentum, you cannot use the traditional formula. The intensity of light and energy of a photon. By the way, when I say energy of a photon, is this energy kinetic in nature or potential in nature, or kinetic plus potential? What do you think? Is this energy, can I write it as half mv square? The answer to that is I can't, because m is 0. So there is no point of writing it as half mv square. So strictly it is not the kinetic energy or potential energy. It is just the energy of the photon. It is the sum of everything. You can just say it is the total energy of the photon. You cannot distinguish what is kinetic, potential. You just call it as the energy of the photon. It's neither kinetic nor potential. It's just the energy. That's all. It's the total energy of the photon. You can't find any bifurcations in that. You cannot segregate how much is kinetic, potential, nothing as such. So let's have a look at some of the questions which may come. Let's say, for example, if a light of 200 watt per meter square, or let's say 660 watt per meter square, and 10 to the power 12 hertz is incident on a 10 meter square area, find the number of photons striking per second. Find the number of photons which are striking per second. Clearly it is an intensity based question, so maybe I'll have to revisit the intensity formula, and let's have a look at the intensity formula which I just wrote it down some time back. I is n by t hf by a. All right, so let's write down that formula. Intensity is basically n by t and hf divided by a. All right, so I want to find n by t. It's very, very clear. So n by t will be I multiplied by A divided by H into F. Fair enough. So let's substitute everything that we know. Intensity is 660. Area is nothing but 10 meters square. H is 6.6 into 10 to the power minus 34. The frequency of light used is 10 to the power 12. A lot of things might get cancelled, as you can see. This I can write it as 66 into 10 to the power 2 on the top in the numerator. This also I can write 66 into 10 to the power minus 35 and into 10 to the power 12. 66 and 66 will cancel. 10 to the power 2 and 10 to the power 12 will cancel. This will become 10 to the power minus 35 into 10 to the power 10, which will then become 1 by 10 to the power minus 25. Take it on the top, it will become 10 to the power 25. So what is this? This is number of photons per unit time. These many photons are going to be incident per second. This is huge. It's bigger than the Avogadro number. It's crazily big. Just imagine this kind of light bulb giving so many photons just in a second, imagine in a year, in a month, in a week, how many photons will it give? Yep. All right. I will just put that comment maybe after the video, Subiksha. I will definitely help you out. Sir, what is W in watt per meter squared? That is watts. Yeah. That is joules per second. 1 watt is 1 joule per second. That unit of power is watt, W-A-T-T. Correct? Yep. Excellent, Rohit. Perfecto. Moving ahead to the next question on your screen. Find the energy and the momentum of light having a wavelength of 300 nanometer. Approximately, you have to find how much will it be of 300 nanometer. All right, so let's try to do this, my dear warriors. Come on, think how will you solve this particular question. First talking about energy, then we will go to the moment. Think. All right, for energy, and let's say we have to find it in electron volt, it will be much simpler. The energy of a photon will be given by 1240 divided by lambda, provided it is in nanometer. I'll get the answer in electron volt. So 1240 divided by 300, the answer will be in electron volt. 300 is already in nanometer. So 124 divided by 3, guys. How much is it going to be? 1010 cancels. No, don't have to use 6.6. Don't have to use 6.6. You can directly use 1240 divided by 300. That will be better, right? Yes. How much is 124 divided by 3? Approximately 41 point something. Approximately 41. Approximately 41. Okay. But there is one more zero. So it will become 4.1. It will become 4.1 electron volt approximately. Approximately it will become 4.1 electron volt. That is the energy of the photon. Usually the answers are given in electron volt, not in joules. Perfect. Similarly, let's also find the momentum of this particular particle, h by lambda. H is 6. Now here we cannot go in electron volt, we have to go in SI units only. So 6.6, 10 to the power negative 34, whole thing divided by 300 nano. Nano is 10 to the power minus 9. So let's see what happens. 66 into 10 to the power minus 35 and here I will write 3 into these two zeros inside, so 10 to the power -7. 66 divided by 3, that is 22. This is 35, 7 goes on the top, this will become 10 to the power -28. So this will be in kg meter per second. So that is the momentum. As you can see, it's very, very small. Extremely small. Can you see that? Yep, very, very small, my dear warriors. Perfect. Very good. So that's how you find that. Very good. Now, all right, let's say if you have to solve this particular question. Say for example, the question given is the momentum of a photon is tripled, then the lambda is going to be dash, the energy of the photon is going to be dash, the intensity, assuming all other parameters are same, is going to be dash. What will happen to each one of them? That is the question. The momentum of a photon is tripled. What do you think will happen to the wavelength, the energy of the photon, as well as the intensity? Let's see if you guys can figure this bit out. It's not that difficult. First, talking about lambda and momentum. Lambda is h by p because p was h by lambda. So if momentum is made 3 times, wavelength will be made 1 by 3 times. Can you see that? Wavelength, because denominator is made 3 times. So this will be 1/3 of the old value. This will be 1/3 of the old value. What about the energy? Well, for energy of the photon, we have this formula hc by lambda. So if lambda is made 1 by 3 times, that means the 3 goes on the top. So the energy of the photon will be made 3 times. So this will be basically made 3 times into 3 times. It will be made into 3 times. Make sense? Because denominator is 1/3. This 1 by 1 by 3, this 3 will go on the top, which will make it 3 times. What about the intensity? If you remember the intensity formula, assuming n by t is the same, you had hf and a. Well, this hf is only basically that energy of the photon. hf only is the energy of the photon. Other parameters have not been changed. So if this becomes 3 times, it's natural the intensity will also become 3 times. So this will also be made 3 times, or this will be also tripled in nature. Got it? How to solve this particular question? Very good. Perfecto. Awesome. So that was your introductory part about photons, where we studied the different properties, energies, and other things related to the photons. Now, when we spoke about the particle nature of light, which was called as photon, and when we talk about light, okay, when we talk about light, you have the photon and the wave characteristics. In wave characteristics, C is equal to F times lambda. Here you write kinetic energy, just the total energy is equal to hf. The momentum is h by lambda. What you can't write is the energy equals to half mv square. This is not permitted. even the momentum is equal to mass times of velocity is not permitted. Also, remember in this case, the photon mass is always going to be 0. The photon's mass is always going to be 0. So these are the characteristics that we have learned till now. It's more like a summary. Now, what a scientist thought is, if light has dual behavior, maybe all the things around us, like the particles, maybe all this while we were thinking they were particles, but maybe they also have the other side, that is the wave behavior. What is there around us is called matter. Exactly. What is there around us is nothing but called as matter, isn't it? And this matter, maybe that too has dual behavior. That too has dual behavior. And what we usually see is the particle behavior of it. What is usually seen is the particle behavior of it. But maybe there is a wave nature also of it. There is a wave nature also of it. That wave nature is then called, because it is of a matter related thing, so why not call it a matter wave? Why not call it a matter wave? This was not a normal wave, this was a electromagnetic wave. There are electric fields and magnetic fields interlinked with each other. This is not electromagnetic, this is matter wave, a new kind of wave they thought might exist, which we usually do not see. Now, when we talk about the particle nature, very contrasting results as compared to the photon. Any matter that you see, me, you, a box, a ball, a chair, atom, electron, proton, neutron, these are all matter. They are made of something, and that we call as a matter. They have mass. Yes, so this particle has mass. This is a mass particle. This is a mass particle. This is nothing but a particle with certain mass characteristic. So for such a thing, the mass is not 0. Mass is there. Mass is definitely there. Talking about the energy aspect of it, the energy of such a particle which is in motion is kinetic in nature. It is kinetic in nature, and that is just given by half mass is there, speed square, half mv square. The speed can be anything. Speed can be anything. It need not be the speed of light. So here photon has to travel at the speed of light, but nothing like that over here. I can throw a ball at 5 meters per second or even 100 meters per second. Talking about the momentum, here I can write the momentum as mass into velocity because mass exists. I will not use this formula, isn't it? So that is one critical distinction between matter and light, as you can see on this particular slide. But then what about the wave characteristics? Can we say something about the wave of this particular matter? Well, it so happens that if you just shift lambda here and p below, that's it. This lambda, which is h by p, then becomes the wavelength of that matter wave. It becomes just the wavelength of that matter wave, which you cannot see, you cannot feel. All right, it's a very, very interesting concept. The lambda of that matter wave is h by p, which is very, very similar formula. And here this momentum is nothing but mass into velocity. Here you cannot put momentum as mass into velocity. Beware of that. In fact, the momentum over here is the energy of light divided by c. Energy of light divided by c. Here the momentum is related to the energy. If you recollect your 11th standard classes, you will remember the momentum was root 2 mk because the kinetic energy itself was p square by 2m. Do you remember this? This is only applicable for this guy, not for here. Yep, square of the momentum by 2m. So 2m taken over here, 2m into p or 2m into k. That will be basically the momentum relationship. Is this absolutely clear? Yep, root 2 mk or root 2 me. This is only valid for mass type of particles. Very interesting thing. Yep. RNA batch is over. Arunachalesh, Arunjan. Yep, it is done. Yep. Okay. Perfecto. Perfecto. Now that you understand, oh, these two things are completely different and when to use what, okay, please remember here, never ever write energy as HF. This is, or let's say HV by lambda. Do not write such stuff. Okay, you cannot write such stuff, HV by lambda. If you write it, 0 marks you will get for mass type of particles. So let's see if you can figure this bit out. A proton of mass m is accelerated by delta V volts, then find its, oh, by the way, I forgot to tell you the name of the scientist who gave this. This was given by de Broglie, so that is why this is also called as de Broglie wavelength. De Broglie. De Broglie gave this formula. He just flipped from here to here and he was able to prove it experimentally also. This thing exists. So this is also called as the de Broglie wavelength of the matter or the matter wave. So find its de Broglie wavelength. Find its de Broglie wavelength. That is the question. Let's try to see whether you can figure this bit out. Now, if you take a proton having a charge of plus E and you accelerate it by voltage difference of delta V, obviously it will gain some velocity. It will also have some kinetic energy. Where will it get that kinetic energy from? Because of this voltage difference, so the electrical potential energy will convert into the kinetic energy, of that proton. How much is the electrical potential energy? It is always, if you remember, the charge multiplied by the potential difference. Do you remember this? Charge multiplied by potential difference. The charge is E and the voltage difference is delta V. So this will be equal to the kinetic energy. Great. So we got the kinetic energy. That will be helpful for us because without that we can't find the de Broglie wavelength. Talking about the momentum is root 2 mk. So the momentum will be root 2 times mass times kinetic energy is E times of the voltage difference. Perfect. Let's go to the final thing. Wavelength, de Broglie wavelength is h by lambda. H is the Planck's constant. Lambda, oops, sorry, what did I just do? H by P, my bad. H by P. So what is P? P is basically this. So it will be root of 2me delta V. So that is your de Broglie wavelength. Is it okay? Yep. H by root 2me delta V. Perfecto. Perfecto. Let's go to the next question coming up on your screen. A photon and a proton of same energy have their de Broglie wavelengths in a ratio which is proportional to the energy raised to which power? This was asked previously in the NEET examination. Let's see whether you are able to think about it. If you take the ratio of the wavelengths of proton and photon, one is light, one is matter, then it is somehow proportional to the energy raised to some particular power. Everything else will be a constant. Yep. Magnetic effects of current already done. Sushmita, I am not sure if you have seen that lecture. It's there on the channel. Yes, it's there on this particular channel. Just search for magnetic effects. Just search for magnetic over here, you will get it. See, moving charges and magnetism, magnetism matter, moving charges and magnetism part 2. All right, EMI, electromagnetic waves, everything was done before. So just go back into the thing, you will be able to get it. Just check my NCERT line by line series, you will definitely get it. All right. Okay, Sushmita, if you are not able to find it, just still drop a message in the comments. I will help you with the link, not an issue at all. Okay, find the ratio of the wavelengths. How do we do this particular question? First, let's do it for the photon part. For the photon, the energy is just hc by lambda of the photon. So I'll call it as lambda 1. So therefore, lambda 1 will be hc divided by E, okay, on the sides. Now let's talk about proton. Well, how is energy and wavelength related to each other? Well, lambda of the proton is nothing but h by p, and the momentum is given by root of 2m times kinetic energy. In this case, it is just E. Now, it is clearly mentioned that they have the same energy. It is clearly mentioned. So, because this phrase has been used, that's why I can use the same energy value here also and here also. So, I won't have to worry about using different values. All right. So, now that I have got this, I will just take the ratio of these two. So, lambda 1, okay, here it will be hc divided by E. And what is lambda 2 divided by lambda 2? It will be nothing but h divided by root 2 me. Now h will cancel, h will cancel. Just see what are we getting. Lambda 1 by lambda 2 is equal to c root 2m, and here I am getting 1 by root e. Root e, and check this out. If you are not able to understand, no issues. This is root e and this is just e. So this will become 1 by root e. So basically this is nothing but c root 2m e raised to negative half, which is then lambda 1 by lambda 2 is directly proportional to e raised to negative half. So options will be like half, negative half, plus 2, minus 2, something like that. So the correct answer to this question is negative half. Yes, minus half. Perfect, Pratibha, Krishna, awesomeness. This is how you solve this particular question based on this. Very good, very good, very good. All right. So this is basically your wave and particles duality, meaning that how light can behave dually, and even mass, which is matter, can also have dual kind of characteristics. So that is what wave particle duality is all about. Now this further led to the discovery of something called as the photoelectric effect. So what is this photoelectric effect? Let's understand it. Imagine you have a surface. Imagine you have basically a surface like this, and this surface obviously will have nucleus and electrons revolving around it, that means atoms, and these dots represent the nuclei. They are intact, they can't be moved anywhere. These dots represent the nuclei which can't be moved, and these red dots represent those electrons which are wandering around it. So this red dot are basically electrons which are basically free in nature. That means if they are free in nature, so whatever thing I have drawn must be something like a conductor, basically a metallic surface, because conductors do have free electrons around them. Why am I talking about free electrons? You will understand in a bit. Now what I do in the next stage, is I will take light and I will make it fall on it. I will take light and I will make it fall on it. So this is your incident light. When this light falls on it, this light will have some energy. Don't focus on the wave aspect, focus on the particle aspect. This light has energy, it has momentum, it can impart force. It's like you are taking water balloons and throwing it on sand. Thup, 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 you're throwing it on sand. Or you're taking some stones and then throwing it on sand. Each stone has a momentum, it has energy. What will happen? The sand particles will spill. It will come out. Zoop. You throw some stone on the mud, some particles will fly in the air. Sand particles will fly in the air for some time. Isn't it? So same thing will happen here. This incident light is just like saying, actually, what is happening is photons of light are basically incident. Yes, photons of light are basically incident on this conducting surface or metallic surface. So these are photons which are incident. So they are also incident photons. Incident photons. Yep. So this incident light is technically the incident photons. What do they possess? They have momentum. They will hit that electron. But remember, these electrons are also tied a little bit. It's not, when I say free, don't think they're completely free. Don't think they're completely free. They're slightly tied to their houses, basically their nucleus. So you will need some effort to pluck them out. And if you have enough energy, then these electrons will start ejecting out. These electrons near the surface will start ejecting out. So these are your ejected electrons, which are then called as photoelectrons. Photoelectrons, because they are ejected because of light. Light means photo. So because they are ejected because of light, that's why photoelectrons. So ejected due to light. Ejected due to basically light. That's why they are called photoelectrons. And these photoelectrons will probably then go in some random directions here and there. Who knows? Each photoelectron might go in some random directions like this. Some electrons will also come from here. So many such photoelectrons are going to be ejected out of this. This scenario is very much similar to, imagine there is a house. Okay. In that you have a very strict parent, and this kid is there. This kid is there, like the electron, who wants to go out and play. So to ask him out to play, a friend comes, which is like that photon. His friend comes, asks permission to his parents. Hey, can I go out to play with him or her? Now it depends how strict the parents are, how good the friend is. If the friend has good convincing skills, some friends are there, you might have seen, they have very good convincing skills. The moment they talk to your parents are okay, yeah, go, you are only there. No, okay, go. But some friends are there, even though it is like buying one stationery item or a book, parents are like, don't go out with this kid. 100% no. So it depends on this guy. The energy, convincing energy of this guy, whether this person will come out of the house or not. So the electron is like this kid over here. The parent is like the nucleus over here. The house is like the atom, you can say, and this particular friend of yours is like the incident photon, is like the incident photon. I hope you are able to understand this. So this electron can be then finally ejected out depending on the convincing skills and the strictness of the parents. Everybody getting this idea and this concept? So photoelectron 𝐂𝐤 is nothing but an electron which gets knocked out because of light. Light's other word is photo. So electron ejected because of light. Light, photo, photoelectron. So photoelectron. Electron ejected due to light is photoelectron. Got it? Awesome. Now, this atom plays a role, this light plays a role. That means this light should be of sufficient energy. But imagine the same friend maybe in some other house might not be able to convince this particular parent. Maybe this parent is very, very strict. So this particular kid might not be able to go out even if that same photon is falling onto it, and you will see nothing coming out. You will see nothing coming out because the parent is very strict. That means the house's environment is very, very strict. So it depends on the metallic surface. So we will see there are actually two characteristics by which you can see how much electrons or in what quantity and how much in number, what energy will they come out with. It depends on the incident photon's energy, and it also depends on the metallic surface characteristic, which is also called as the work function of the conducting material or the surface. The work function is that minimum energy which is required. Work function is that minimum energy which is required to pluck that particular electron out. So imagine your friend over here came with 70 units, laddus of energy. Convincing power is 70. The parent needs only 40 units of energy to release the kid. My God, we are talking as if the parent is a jailer, but okay, anyways. The parent needs 40 units of convincing energy. So out of 70, 40 will be used to convince. What will happen? The remaining 30 will be there with the kid. The kid will be in full josh. Yay, I got permission. He will start running. He'll start running. But imagine now, another friend comes the another day. He had 100 convincing power, but your parent needs only 40 convincing energy. What will happen to the electron which will come out? This friend was even better. The moment that friend came, oh my God, this friend has come. Learn from him. Go with him. Run. So this kid will start running with 60 units of energy, even faster. Very excited. Got it? Everybody understood? But imagine that same friend, Papa went to another house one day. There the parents are super duper strict. 90 units of strictness, 90 units of energy is required to convince them. This kid, after so much convincing, please leave. It's okay, I will come back in time. I'll come back before 8 o'clock. No worries, Uncle, I will keep him safe. No problem. We are going here only. This, that. Finally, he'll get fed up, and when he comes out, he'll be full low of energy. 10 units of energy will be there. Got it? Everybody understood how this works? Yep. ESU, I have taught it in NEET NCERT line by line ESU. You can check that out. Yeah. So I hope this example was very, very clear. Now, what might be happening here? If 70 comes, this friend comes, 70, he has convincing power of 70. This parent has convincing energy which is required of 200. 70 is coming. Parent will be like, hey, you came with 70. I need 200 amount of convincing power. Poda, get lost. What are you doing? So nothing will come out. 0. Next day, another friend comes of 100 units of convincing power. Parent will be, hey, you didn't learn, huh? I need 200 units of energy. Go. Zero. Nothing will come out. But someday, principal's kid only came. School principal's kid only came. That guy has next level aura. He has 250 convincing units. Then this parent will get convinced. Oh, principal's kid, 100%, amazing kid. Go out with that kid. 50 units of energy will be there with that electron while going out. Got it? Yeah. Understood, guys, how this works? This is basically photoelectric effect. This is what Einstein did, and he got Nobel Prize. He will be like, sir, Einstein got Nobel Prize for this, sir. This is my daily story, sir, in my life. One day this, 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 one day this. I don't know which kind of kid and house are you going to be in. I don't know. For my daily life story, Einstein won Nobel Prize. I feel like crying in the corner, sir. Anyways, so coming back over here, and yep. So there is a simple energy equation which I will write. The energy of any photon will be utilized in two ways. First, to convince the parents, that is the nucleus, hey, please give me the electron. That is called as the work function. This is called as the work function phi, work function. What does it depend on? It depends on the material. It depends on the material which is there, whether it is aluminum, silver, nickel, cadmium, it depends on that. And the remaining part will go in the energy of the electrons, which is nothing but the kinetic energy. This is the maximum kinetic energy which those electrons can have, because maybe some electrons will lose energy, so some energies might be lost, but maximum energy which it can get is K, which is right over here. So this equation is basically called as your photoelectric equation. This equation is particularly called as your photoelectric equation. Everybody clear till this point? रियल में बहुत कम निकल पाता है. Yes, these are very few in number. See, like you can see, some electrons will be trapped inside, no? Tup, 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 they will collide here, there and all. Not everything will come out. So actually there is a deeper story. If you want to make it more complex, then it is like this. Even when the friend got convinced, this kid became very happy. Sorry, the parent got convinced. This kid became very happy. Yay, I got permission. Yes, I got permission. Okay, wait a minute. I will pack my bags. He runs up. He will pack his bags. Okay, I need this. Okay, I need that chocolate. I need this book. Okay, I need this bag. Okay, I need these shoes. By the time it comes out, full excitement only down. Oh, I'm tired. It's okay. You go, man. I won't come. It's okay. It's okay. Okay, please go. It's okay. Okay. Dude, you just got permission. No, it's okay. I got tired, man. So that also will happen. That also will happen. But few kids will be there. Permission gone. I am wearing half pant. I am wearing banyan. I will leave. That's all. They won't bother. What am I wearing? What am I not wearing? They will just leave. So that will be having maximum energy. They won't waste a minute also. Zoop, they are out. I don't, before my parent changes my mind, I'm out, man. I will buy a shirt on the way. It's okay. I will come in the banyan, but you don't give me one more minute also. That is what it is. Got it? Loud and clear? Kum, understood? Awesome. Okay. Now, what is the value of this phi and all of that? See, if you use red light, okay, if you use a red color light, this has large wavelength. The wavelength is large. The frequency is less. the energy of the photon is less, that means the convincing power is less. So even when it falls on the surface, it's very likely the energy of the photon is so less that maybe no photoelectric effect occurs. So maybe no photoelectric effect occurs. But maybe then you change the wavelength to maybe yellow, which has a slightly smaller wavelength. Now you see photoelectrons are getting ejected, definitely. Wow, you are happy. Then you use violet or blue color of light, which has even smaller wavelength, The wavelength is small, the frequency is more, so the energy of the photon is also more. That means that kid who will be convinced will have a lot of energy when it is ejected out. So the kinetic energy will also be more in amount. So probably yellow is the color when the switchover happens. This is just an example. Don't think always yellow is the color. This is just for example's sake. So this is that critical wavelength lambda naught or critical frequency f naught for which the energy of the photon just equals to the work function, and there is no or very negligible amount of kinetic energy. So very small kinetic energy is there. So just eject it out. So this is then called as the threshold. This light is the threshold light, threshold wavelength, threshold frequency, and that's how you derive the work function. So energy of the photon is hf naught. You can also use hc by lambda naught, which is also phi, which is nothing but your work function, Okay, so this is the formula, and I can then say if by any chance the frequency is lesser than or the wavelength is more than lambda naught, frequency is less than f naught, then there is no photoelectric effect. This is very important. If it is less than that, okay? But at the same time, over here, if the frequency is more or the wavelength is less than the critical frequency, which is threshold frequency, or the critical wavelength, which is the threshold wavelength, then their photoelectric effect occurs. Photoelectric effect occurs. Got it? So you need at least f naught frequency. Yeah. So to be very clear, if the light does not have sufficient frequency, basically sufficient energy, just like over here, the light does not have sufficient frequency or energy, then it will not be able to conduct the photoelectric effect. But only when it has sufficient energy, it will be able to take out that electron. For this house, 40 becomes the work function. In that another house, 90 is that new work function. The strict house, 200 is that work function. You need this many units of energy to basically take out or pluck out that electron. That means that kid over there. So that minimum frequency for which the photoelectric effect occurs, or the maximum wavelength till which the photoelectric effect occurs, is called as the threshold frequency and the threshold wavelength. Is that absolutely clear, everyone? All right. Gravitation in Rohr series is done. Rohit, don't check the live section, check the video section, it is there, or check the playlist. All right. Is it clear? What is the exact definition of threshold frequency? The exact definition of threshold frequency is, if you want it formally, the frequency after which the incident light is able to conduct the photoelectric effect, and the photoelectric effect occurs, that frequency is called as the threshold frequency. All right, the frequency above which the photoelectric effect occurs, that frequency is called as the threshold frequency. So F more than this critical frequency. Absolutely clear, everyone? Yep. Kumkum, what was your doubt? Not sure. Yes, that chapter is covered. So Smita, I'm not sure exactly NCERT, but the photons, duality, and photoelectric effect, not the atoms part. Atoms part is a separate thing altogether. Okay, so let's go to the next part. We have talked about energy of the photon and this thing. Now help me understand, will this be affected by more photons being incident? The answer is no. Just because more light falls does not mean, say for example red has very low frequency, very high wavelength, so very less energy, so it is not able to conduct the photoelectric effect. So if more light falls, will the photoelectric effect occur? No. So it is not going to be affected by the intensity of the light. If the frequency is less, doesn't matter, you make the earth upside down, that's it, photoelectric effect will not occur whether the light is of low intensity or high intensity. As simple as that. I'm so glad, Dinesh, you loved it. So glad. All right. So ray optics I have already taken, Dhanushri. It's done in the express batch today itself. We have started it. Number 2, if you're talking about NCERT line by line, that is also done. Ray optics part 1 and part 2. Just check the NCERT line by line series. It's done, yeah, in the YouTube on NCERT line by line, and in the batch, I've just started the lecture in the station 1. The batch has started today. This is station 0. Station 1 is on the batch, which is on the platform. Yeah. Okay. Now, imagine if less intense light is falling, onto this metallic surface. So probably you will see less number of electrons being ejected out. So if somehow these electrons were collected on the other side, okay, there is another plate, and then you conduct a circuit and you have an ammeter of sorts. Somehow if you are able to collect these electrons, okay, which are on the other plate, and you complete a circuit, then you will see, you can measure the current. If you change the intensity of the light from less intense to, let's say, more intense light, you will see more number of electrons will be ejected out. That's very, very important. So basically, I can say that intensity of light, what does it do? It basically increases the number of photons which are incident per unit time. In turn, what does it do? It is directly proportional to the number of photoelectrons which are ejected per unit time. If 1000 of them are falling, maybe some 200 are coming out. So if 2000 fall, then maybe double will come out. So it will be directly proportional to the number of photoelectrons which are coming out. This in turn, because more electrons will be collected and it will complete that circuit, it will be proportional to something called as the photocurrent. Yep, it will be proportional to the photocurrent, the current which is flowing in the circuit because of the photoelectrons is then called as the photocurrent. So I can definitely say that the intensity of the light is directly proportional to the photocurrent. This is a very, very important relationship. Not just that, there is also a graph related to that. You might have seen this in different PYQs as well. Here you plot basically the intensity, and on the y-axis you plot the current, and this particular graph just goes like this. It's just a straight line. Yep. And it passes through the origin because when there is no light, obviously there will be no current. So it is just a straight line passing through the origin. Is that right, everyone? Did you got it? Okay, perfect. This is another important thing. Oops, I think I needed one slide here. Next important thing. Imagine this was the metallic surface onto which the light was incident, and the photoelectrons which were ejected, they were collected by another plate over here, and then you just completed this particular circuit. And while you completed this particular circuit, you are measuring the current through it. You are also measuring the voltage across the plates. But this can be done in multiple ways. Look at this now. This can be done in multiple ways. Here, I am just connecting, here I am just connecting the wire. This type of setup is called as no bias. There is no bias to it. That means there is no polarity associated here. No partiality is there. Bias means partial. I'm not being partial to this plate or this plate. But next, I will make it biased. I'll tell you how. See, if the electrons are going here, it means the current is going like this. It means the current is basically going anti-clockwise. Current is the flow of positive charges, opposite to the flow of electrons. So imagine you make this side positive and this side negative. This is basically forward bias. You are helping the current. This is your forward biasing. And then the exact opposite, the current, because the electrons are going clockwise, the current would be going this way. The current will be going this way. So you do exact opposite biasing. You oppose the flow of the current. You make this positive and this negative. This is your reverse biasing. You are opposing the flow of the current. These are the three biases which are going to happen. And let's see in all these biases what kind of behavior you can expect. See, bias is like, if you talk in terms of this particular example, right now this is an unbiased thing. Bias means something like a cheating. Something like a cheating. Imagine this was your dad or mom. Imagine the other parent. The other parent or some other auntie, or your parents are here. Some auntie comes from the neighbor. The auntie is like, yo, papa, kid, he's asking so much. What, you won't leave, huh? Go, let him go. So you help. So even then, so when you help, what will happen? What will happen? This kid will go with more josh, will go with more energy. Maybe remember that kid was there who was very, very tired because he ran around the stairs and he was packing all his stuff and all of that. So imagine that kid got tired, but then some auntie came, some another friend came and like, hey, papa, kid, yeah, let's go. Hey, go, man. Why are you saying no? Go. So you're helping. That is forward bias. But then some relative comes and says, yo, you are sending your kid here also? I thought don't send by my kid. Oh, you don't know what these kids do these days. Don't send. You also keep quiet. Papa, that parent had agreed. A friend had convinced, some person came and told, hey, don't send, gone. This guy, full disappointment, full demotivation, gone, sat in the house. So that is reverse biasing. From external factor, bias, partiality has been created. So this will create, when you have no bias, what usually happens is you will see that there is a very small current, very small current. The reason for that is because not all electrons make it to the other plate, and even outside the metallic surface, even outside the metal surface. Not all the electrons are able to come out of this surface. If 100 photons fall, maybe out of 100 photons, maybe only 20 photons were successful in taking those electrons out. The remaining 80 were unsuccessful because those electrons collided, they lost their energy inside that metal only. So that is very bad. Only 20% efficiency is there. Is that right? Okay. Very good. Awesome. Okay, great. Now, in the forward bias, what will happen? This will be more current, and the reason for that is because those electrons which lost energy are pushed, or basically pulled to the other side, So because of which you will see there is more current. But there is a problem to this also. Imagine 100 photons were falling earlier. Only maybe 40 electrons were reaching here on the other side. Now what happens? Out of that 100, because you have kept a battery in the forward bias, instead of 40, maybe 60 will come. You will be very happy. Then you increase the voltage of the battery, you make it even higher voltage. Then instead of 60, 80 will come. Then you get more excited, you make it even more volts. Then what will happen? 100 will come. You get even more excited, you increase the voltage. Do you think 120 electrons will come? No. How is it possible? Imagine 100 friends came to 100 houses. Obviously, only 100 kids can come out. Do you get this point? If 100 friends enter, or let's say 200 friends enter into 200 houses to convince 200 parents and their kids, maximum 200 kids can come out. Suddenly 300 kids are coming out, you will be like, hey bro, 200 kids went, no, to convince 200 parents. Where are these 100 extra kids coming from? From where did that extra enthu come? What, these parents only kicked out these kids, huh? That's what you will think, right? So that can't happen. Are you getting my point, my dear warriors? So that is the reason why beyond a certain limit, you can't exceed this. Yes, you can make it maybe 70, 80 and all that, but it reaches saturation. It reaches what? Saturation. Very important. It reaches what? Saturation. Very important. Great. In the reverse bias, this current reduces as it is opposed by the battery's voltage. So it's like that neighboring auntie who does kirik, or uncle who comes and does some kirik, kida, right? Full kida, kirik thing. Hey, why are you sending your kid? They will get spoiled. But then your parents and you are like, no, I will not do all these things. Don't worry, I am fine. So if you are able to overcome that quickness, you can still go out with your friend. But imagine that uncle is so quick, that auntie is so quick. Like, don't send ba, you don't know what is this. See, I'll show you this WhatsApp message. See what is happening. Oh my God, look at this. See what is happening these days in the world. Oh my God, oh my God. That's it, gone. Oh, okay. No, that uncle is saying correct only. You stay. Don't listen. Hey, you also go, man. Let this kid also stay here. So you are putting a stop to it. So the current is opposed and it reduces until it becomes completely zero. And when that completely becomes zero, that voltage is basically called as the stopping potential. The stopping potential. Now it's very easy to measure the stopping potential. So the stopping potential will be the maximum kinetic energy of those electrons, will be the maximum kinetic energy of the electrons. So stopping potential into the electron charge will be the maximum kinetic energy. Charge into voltage is energy. This energy will be the kinetic energy. So this is a very, very important looking formula. Very important formula. Got it? Awesome. Okay, guys, don't spam or else you'll get blocked. Yes. Now you can draw a graph showing all of them together where on the x-axis, and this is your y-axis. This is 0. This is your battery voltage. So whatever is on this side will be forward because it is positive. This side will be negative, so reverse bias. Okay, and on the y-axis, what will we have is basically the current. How will this graph look like exactly? So this is how it will look like. Observe it carefully. When there is no bias, the 0 means there is no bias over here. There is a very small value of current, so the current will be very small. When you go to forward bias, the current will increase, but it will reach a saturation. And over here, you will see probably it will go till this point. So this voltage is on the negative side, so negative 5 volts, negative 4 volts. So that 4 volts becomes the stopping voltage, that 5 volts becomes the stopping voltage. Okay, I hope this is absolutely clear why this graph is like this. It goes, increases, and then it becomes saturated right over here. Beyond this, you can't pull out more kids than what is asked for. So this is basically your saturation current. Saturation current. Is this absolutely clear? Beyond a certain voltage, you can't increase the current. Now, if you draw the same graph for different intensities, it looks something like this. If this is for intensity, let's say I1, you can increase the intensity of the light, but the stopping potential which is there, that won't change. Because how does intensity of light even matter? It will just increase the number of photons, number of electrons, hence the current. But increasing the intensity does not mean increasing the energy of the photon. That means I cannot change the kinetic energy of the photon. That means I can't change the stopping potential of the electron. So definitely it won't be affected. So even if I increase the intensity, this is what I will see. Here the intensity I2 is more than I1. Current will increase, but stopping potential remains the same. Increasing intensity, increasing the intensity increases the photocurrent, but doesn't affect, what doesn't it affect? The energy of the photon or the kinetic energy of the electron and because it doesn't affect that, therefore even the stopping potential remains basically the same. This is a very, very important outcome that you can see. I hope this is absolutely clear. Thank you for reminding me to have water. Thank you so much. Thank you so much. Perfect. Now, if you rewrite our photoelectric effect equation, let's revisit our photoelectric equation, which was energy of the photon, right, is equal to the work function plus kinetic energy of that electron. Now, in general, energy of the photon can be written down as hf. The work function, I have told you this right over here. I can write it as hf naught, where f naught is the critical or threshold frequency. So I can write it as hf naught. And if you talk about the kinetic energy, we just saw that kinetic energy can be written down as voltage of stopping it into the electron charge. So I can just write over here plus E into Vs. This is a modified version of it. You need not have to really by heart it, but it is very obvious how we get it. So we have just revisited the photoelectric equation, nothing much. But I can further play along with it and you will see how. Let me just shift few terms. So this will become hf and this will become minus hf naught is equal to E times of Vs. Therefore, check this out, Vs will be equal to, check this out properly, hf and here minus hf naught, because I have divided the whole equation by E, so it will be h by ef and h by E f naught. Perfect. Now keep this equation aside. If you want, we can also further rewrite it like this. Therefore, Vs will be, observe this carefully, h by E times of f, and this is nothing but minus phi by E, minus phi by E. Why did I write it like that? Observe now, you will see. Let me draw the x-axis. Let me draw the y-axis. On the x-axis, what I will have is the frequencies. I'll have the frequencies. And on the y-axis, we'll have, correct. Y-axis will have the stopping potential. Perfect. What you will notice, this entire equation is just like y is equal to, just check this out, mx plus c. Are you able to see that? Where the slope m is h by E and the y-intercept is basically, negative phi by E. X is just like your frequency and the y-axis is basically like your stopping potential. Y is equal to mx plus c. So this graph definitely must be a straight line with negative y-axis intercept, So if I have to draw it, obviously I'll have to show it like this maybe. And it will maybe hit over here. Now, if I take some other metal or other surface, the f naught or the phi value, work function will be different. So the intercept will change. So for that other metal, maybe it will be like this, and maybe it will hit this graph somewhere else only completely. But you know what will be same for all of them? The slope which is going to be h by e is going to be the same for all the graphs, all the materials, no matter what you draw. Very, very important. Who is this? Nanda Kishore, unnecessarily you are spamming, disturbing the students, you will be blocked. Okay, anyways, coming back over here. This y-intercept is right over here. This is your negative phi by e. If you use a different material, the phi will be different, so it will hit it differently, but the slope will be same. This graph was also asked many times in your NEET examination. You can check out the papers. So these are the important things regarding the photoelectric effect. This graph, then the intensity and current graph, and stopping potential, work function, and all of that. All right. So I hope you have understood this photoelectric effect, wave particle duality, and the photons theory, and how it is different from matters. All right. So like I said, there will be problem solving sessions which will be starting off next week. What are the exact details? What's the schedule like? Everything. That's your express version only. Yes, our NEET Express series will continue, but in a very different form. The entire new avatar will be revealed by the weekend. So stay tuned on the channel. Make sure you are liking this video. Make sure you're subscribing to the channel. Make sure you're also commenting below that, yep, this particular chapter was done, or this particular topic was done. Photons done and dusted. Okay. Take care, guys. Have a great time and good night. I'll be seeing you very soon. Thank you for liking. Yeah. And if you want to study the entire syllabus under me, then remember the batch has just started today, which is called as the Station 1 of NEET Express. The link for that is there in the description box, and this is there in your 3 versions: Prime, which is affordable for 2,999, Combo with the test series couriered at your doorstep for 4,499, and Pro with the test series with the hard copy of the material and doubt app also access for 24/7 doubt solving, 8,999. These prices are introductory prices which will go up after some time. So before it goes up, make sure you are a part of it. That's all I will say. The entire detail about this particular batch has already been given to you in this particular orientation session. If you have not watched it, please check this out. You will get the complete details of how the batch structure and the working is. Okay. Bye bye. Have a great time. Thank you for liking.